Hello friends, I welcome you in lecture number 40 on Laplace transform. In this lecture we will discuss convolution theorem for inverse Laplace transform. We have discussed convolution theorem for Laplace transform in lecture number 39. So we first recall that result. We know that if we have convolution of two functions f and g, then Laplace transform of convolution is given by product of their Laplace transforms. Laplace transform of f star g equal to Laplace transform of f multiplied by Laplace transform of g, and we use these notations for Laplace transforms. Laplace transform of small f is denoted by capital F of s, and for small g we use capital G of s. From this we can write the convolution theorem for inverse Laplace transform. Because Laplace transform of f star g is capital F of s into capital G of s, we can say that inverse Laplace transform of product of capital F and capital G is equal to f star g, which we can obtain using the definition of convolution. This is equal to f star g, which is a function of t, and we know the definition of convolution. It is integral of f of u g of t minus u with respect to u from u equal to 0 to t. We can use this convolution theorem for inverse Laplace transform to obtain the inverse Laplace transform for product of two functions of s, and for that we must be able to decide inverse Laplace transform of capital F and inverse Laplace transform of capital G. Suppose inverse Laplace transform of capital F is small f, inverse Laplace transform of capital G is small g, then we can obtain convolution of these two, f of t and g of t, using the definition of convolution. So they can ask you to write down the convolution theorem for inverse Laplace transform, and you can write in this way: if inverse Laplace transform of capital F is small f and inverse Laplace transform of capital G is small g, then inverse Laplace transform of capital F into capital G equal to convolution of f and g, and this is equal to integral from 0 to t f of u g of t minus u. Integral has limits u equal to 0 to t. We can find out inverse Laplace transform using convolution theorem. So we do this question which was asked in GTU Winter 2019 exam. Using convolution theorem, obtain L inverse of 1 divided by s times s square plus a square. And same type of question was asked in GTU Winter 2009 exam by taking particular value of a. If we take a equal to 2 here, we will have a square equal to 4. So they can ask in either of these two ways. So this is for particular value of a, this is in general. And we have to apply convolution theorem to obtain inverse Laplace transform of this function. Given function is 1 by s, it is 1 by s into s square plus a square. If we want to apply convolution theorem, we should write our function as product of two functions whose inverse Laplace transform we can find out. Here I am writing this given function as product of 1 by s and 1 by s square plus a square. Now I can choose any of these functions as capital F and any of these functions as capital G. So suppose I consider this function as capital F. So I am writing in this way: 1 by s square plus a square into 1 by s, and this is equal to capital F of s into capital G of s where we have taken capital F of s equal to 1 divided by s square plus a square, and capital G of s is 1 divided by s, and we are interested in the inverse Laplace transform of capital F of s into capital G of s, and by convolution theorem we have inverse Laplace transform of capital F into capital G equal to convolution of small f and small g. So first we have to decide small f, which is inverse Laplace transform of capital F, and small g, which is inverse Laplace transform of capital G. So first we obtain inverse Laplace transform of these two functions. F of s is 1 divided by s square plus a square, and we have ready-made formula for this, L inverse of 1 by s square plus a square, and here I can write it is inverse Laplace transform of capital F of s. This is equal to, and we have ready-made formula for this, sin 80 divided by a, and this we denoted by small f of t. Similarly, we write inverse Laplace transform of capital G, and it is equal to inverse Laplace transform of 1 by s, and inverse Laplace transform of 1 by s is 1, and this is denoted by small g. So we have inverse Laplace transform of capital F and capital G. Now we can apply convolution theorem. So using convolution theorem, we are interested in the inverse Laplace transform of capital F into capital G. By convolution theorem, this is equal to convolution of small f and small g, and by the definition of convolution, this is going to be integral from 0 to t f of u g of t minus u integral with respect to u. Now we substitute values of small f of u and g of t minus u. F of t is sin 80 by a, therefore f of u is sin au divided by a. So that we write here sin au divided by a, and g of t is constant function 1, therefore g of t minus u is also 1. So we have g of t minus u equal to 1, so we have to integrate only this sin au. Now integral of sin au is minus cos au divided by a, and there is already 1a, so we write a square. Limits of u are from u equal to 0 to u equal to t. First we take u equal to t, that is minus cos 80 divided by a square. This is for upper limit u equal to t, minus of this at u equal to 0. So negative negative positive, cos 0 is 1, and we have 1 by a square, and this we can rewrite as 1 minus cos 80 divided by a square. Left hand side is inverse of f of s into g of s, and now we can substitute values of f and g, and we have obtained inverse Laplace transform of 1 divided by s into s square plus a square, which is 1 minus cos 80 divided by a square. So this is very easy. You just first write your function as a product of two functions whose inverse Laplace transforms we can obtain, or we are able to obtain inverse Laplace transform of these two functions. Then we obtain inverse Laplace transform of these two functions, and finally we apply convolution theorem inverse Laplace transform of capital F into capital G equal to F star G, and then we use the definition of convolution to obtain the required inverse Laplace transform.